Start out with traditional. Are there any questions?
Yes.
All right. Chapter 6?
No, from chapter 7.
All right. Any questions on chapter 6 to start with?
28. I understand like how you get that. I don't understand how you got the answer. I understand the answer, but I don't know how you got to it.
Which number again you said?
28.
28, the 2 kilogram blob.
I think so. Yeah, I understand the answer, it's not how, like you wanted, I don't know how you want us to write it. Like I didn't understand how the work was done to get the answer.
Oh. All right, so we'll just talk about it. So 6.28.
So conservation of momentum is the key here. Any collision in physics at this point, you should think momentum is conserved.
Which means that my initial is equal to final. So initially we have two objects though. We have two 2 kilogram objects. One's going at 3 meters per second. So let me just draw the picture. So I got a 2 kilogram object traveling at 3 meters per second. And another one at rest. So just go through and figure out what the momentum is. So what's the momentum of the one that's moving?
6 kilograms meters per second.
Yep. And what's the one not moving?
Is it 0 kilogram meters per second?
Yep. All under this idea that momentum is mass times velocity. So 2 times 3, 0 times 2. So what's my total beforehand?
6 kilogram meters per second.
Thank you. Yeah, because total, just adding. So after the collision, what's my total?
The same thing.
Yeah, that's the whole idea of conservation of momentum. Whatever I have beforehand is what I have afterwards. The difference is that afterwards, I have only one object. It's one giant blob of 4 kilograms. So this is my before and after total. And after, it's 4 kilograms times how, whatever the velocity is. And so divide by 4. And you're left with 1.5. Now, did that actually answer your concern, or, okay.
Because the answer made sense, but I don't know how you got to the answer. That was my question, but yeah, that makes sense.
Okay. Other questions from chapter 6? All right, chapter 7. Which one? Chancy.
Let me, it's the spring problem. I couldn't find the
spring problem. Scale.
And could you also do 45 for chapter 7?
All right, so 45 and the spring problem. Do you know which number that is?
I'm trying to find one of them. You can go ahead and do 45 while I try and
All right.
find one.
So Nellie Newton applies a force of 50 newtons to the end of a lever which is moving a certain distance. If the other end of the lever moves 1/3 as far, show that the force exerted was 150 newtons. At least I wasn't wearing the shirt. This is basically a conservation of energy bit. So we have a lever that's getting pushed down with 50 newtons of force, and it gets pushed down a certain distance. So, and at the other end, this is, the way it's worded, I think is awkward, but yet I still put it in the eligible category. Think of it as in what weight can be lifted at the other end. Because it has to exert at least that amount of force in order to move it, of whatever that weight is. Now, they were vague on one bit of, it moved a certain distance, and then the other lever moved 1/3 as far. They don't tell us what the numbers are, so we can make up numbers just so long as this is, the distance this moves is 1/3 that distance. So I'm just gonna make that 3 meters, and make that 1 meter. So she's putting energy into the system, so the system has that amount of energy to burn. So, well, the amount of energy she puts into it is equal to the work she does, and work is force times displacement, which is 50 newtons times 3 meters, which is 150 newton meters, or joules. Meanwhile, at the other end, it's exerting a force on something. It's going to move a 1 meter, and so the question is basically asking the force times 1 meter is equal to 150 joules. So, doing the fancy math here by dividing by 1 meter, the force would have to be 150 newtons. That's what it's going for. So the energy put into the system is the energy that the system now has to get out to something else. Did you figure out what problem it was?
I couldn't find a problem that actually uses the spring constant in what we talked about last week. But I was just assuming that we would have a question like that on the quiz, and I couldn't remember how to do it.
Oh, well, I mean, it's the whole bit with that is that the spring, the potential energy that's stored in a spring is equal to 1/2 times K delta X squared, where that's how far it's displaced off of its just natural state. And K is the spring constant. And again, if I put energy into a system, there's one of two things that are gonna happen. One, I'm either gonna change, let me make sure I word this correctly. If I put energy into a system, there are a couple of things that could happen. The potential energy of the system could change, kinetic energy of the system could change, or it takes that energy and it does work with it. It does something else. So if it happens to get stored as potential energy in a spring, this is basically what we're working with right there. So for replay, I have a 5 kilogram mass cruising along at 3 meters per second, and it hits a spring of with K equal to 10 newtons per meter. We can figure out how much it compresses, the fact that I have kinetic energy in this object here. And when it hits the spring, it's basically that work being done is transferring energy from kinetic into potential. And the only potential that we have here of any note is the potential in the spring. So we start out with my total energy, it's just always kinetic plus potential, is 1/2 times 5 times 3 squared. And I apologize for not giving you a chance to do that in unison. Plus my potential, which is 0, because it's all in the movement here. Oh, I had to go with odd numbers, didn't I? Is that 22.5? And so now I have this amount of energy to do something with the spring, and it's gonna transfer it from this kinetic into that potential. And so to figure out how far the spring compresses, it'll be 1/2 times 10 times how much it compresses squared. So delta x squared is 4.5. So it'll compress 2 and change, 2 point something meters. How about 2.2 meters? Whatever the square root of 4.5 is.
Yep, thank you, that helps.
Yeah, the spring potential, I don't know if he does get into that in chapter 7, he definitely gets into the spring stuff later on. Sort of a sneak peek. Any other questions from 6 or 7?
Oh, I actually did have one more.
Okay.
This is from the Master Set 7. What is the rest energy of a 40 kilogram box? I couldn't figure out how to find that from anywhere in the chapter.
Oh, rest energy. I made a reference to it early on when I first introduced energy. It talked about kinetic potential and rest. It was mainly a side note, and that's sort of a side note question. It's straight plug and chug into the formula. Rest energy, E equals mc squared. So the rest mass, which is the number that I gave you, I think I gave you the mass, and then the speed of light squared, which is approximately 3 times 10 to the 8th meters per second. Because the question you said was just, what is the rest energy of a,
Yeah, it was a 40 kilogram
Okay.
box.
yeah. So it's a plug and chug. Typically, rest energy is not really mentioned until later on, until after, when you start getting into relativity and things like that. That's the point at which it was figured out mathematically at first, the relationship between energy and mass. Other questions from 6 and or 7? Rebecca is saying no. And right now I'm beginning to believe her because no one's asking anything. I came out wrong. I'm continuing to believe you. All right, let's get this done. Let's get it done. Sorry about that.